Now let's have a closer look at different ways of multiplexing in GSM. I already showed you the basic idea of multiplexing on a very high level. For example, the separation of a downlink and an uplink. So we have a so-called paired band. So we use the same bandwidth for the downlink here as we use for the uplink. This example I show you now is one for GSM at 900 MHz, but it works the same way for the other carrier frequencies. I already explained that we use here frequency division duplex to separate the directions. Additionally, we introduce many channels on the downlink, channels on the uplink. In this example, 124, the classical GSM channels at 900 MHz. And for example, some authority can say, okay, the lower, whatever, 62 channels I will assign to operator A and the upper 62 channels to operator B for the uplink and the same for the downlink. That's the basic idea of separating different networks of different operators. So we separate the direction uplink downlink using FDD. We separate different operators using FDM. But now one of the basic questions was, how do we separate different uses of the same operator using the same channel? We assign the channels here to different cells, so each of the cells has a certain subset of the channels. Neighboring cells should not have the same frequencies to avoid interference. But now let's have a closer look at one of the channels. So if we take a single channel in GSM, the system then uses TDMA, so time division for multiple access. The system has so-called TDMA frames consisting of 8 time slots. Frame duration is 4.615 milliseconds. Strange number, but that's the way it is. So 4.615 milliseconds. In each frame, you will see 8 time slots. Now, let's pick time slot number 3 in this example. Then we could, say that a user gets this time slot. So in each of the TDMA frames, slot number 3 is for Mr. Miller and slot number 4 is for Miss Smith, whatever. So this is the first way how we can separate uses. We assign repeating time slots to certain uses. It is a fixed TDMA pattern, so it's not demand driven, but it's a fixed pattern. So once you have time slot number 3, you can always access time slot number 3. And this time slot is now reserved for your call. It's circuit switched, so we set up the call, then we assign the time slots, and then we can use the time slot number 3 or whatever until we tear down the whole connection. So that's the basic idea. Within each time slot, we will see an additional structure. So this is what I show you here is the so-called normal burst. It's called a burst of bits. First of all, you will see, okay, we do not really use the whole time slot. So there's a guard space at the beginning and a guard space at the end. And then in between, we have a certain number of bits, 114 user bits. So 114 bits for the user, repeating every 4.615 milliseconds. So that's the maximum data rate, so to say. So first of all, guard spaces. So why having guard spaces? Why not using the whole slot for transmitting data. Well, think of a setting where you have the BTS somewhere, and then you have a mobile station close to the BTS and one mobile station further away. Now, one mobile station uses time slot, for example, number 2, and the other one uses time slot number 3. What is quite obvious is that it takes more time for the signal to travel from the station further away. Now, the point is that the system has to adjust the sending time according to the distance. So why having additional guard space? Well, the device is moving. You also have things like certain multipath propagation, all the other problems. But while you're moving, you cannot make sure that the user data exactly fits into the slot. Well, if it fits somehow, but there might be some overlap without having the guard spaces. So you cannot really adjust everything. So the guard space makes sure that the data you send from a mobile station to the BTS will not overlap in time with another time slot. So you can shift your burst of bits inside the slots back and forth a little bit. So that's one way of handling the distance. But this will not help us, when you travel further away, you're coming closer to the BTS. So this is why, in addition, you have a field called time advance. Time advance is a certain number of bits where you can actually adjust not the distance but the time of sending. That means if you move further away from the BTS, you will send earlier. And the number of bits is limited, and each bit represents a certain distance, let's say something like 400 meters. And if you set all the bits, then this means you are at the distance of roughly 35 kilometers. So this is why we have this limit of roughly 35 kilometers in the GSM network. Because if you're 35 kilometers away from the BTS, the time advance is at its maximum, and you have to send your data really early so that it fits into the slot structure of the TDMA frame at the BTS. And how do you recognize the distance? Well, the BTS also sends you data. And you will notice a certain shift in time in the received data. And this will tell you the distance. The further away you are, the more this data is delayed. And this means you have to increase the time advance field. If you move closer, you have to decrease the time advance field. And if you're really close, then the time advance is at 0 and your data will exactly fit into the time slot. So time advance is the field. It's a bit vector in your mobile station, and this bit vector reflects the distance of your mobile station to the base transceiver station, to the antenna. And so this is why we have this 35 kilometers as a maximum, because you have a maximum number of bits in the time advance field, and if you set all the bits, that's the maximum. There is a trick to double the distance. Well, as soon as you reach 35 kilometers, you then set again the time advance field to 0, and then your data will jump into the next time slot when it's received by the BTS. You can only do this if the following time slot is empty. But for example, at the coastline, you can easily double the maximum distance up to 70 kilometers because you don't have that many customers, subscribers there. So that means you set time advance against to 0, and your data will be received by the BTS in the following time slot. That means more or less the wrong time slot, but if this is empty and the system knows this, you can double the distance. So that's one of the ideas how you can extend the distance if the signals are still strong enough. So you separate users by using this TDMA frame with its 8 time slots, and you assign a certain time slot to a user. You need guard spaces, well, to adjust for smaller fluctuations in the distance between mobile station and BTS. And additionally, you have a time advance field where you actually tell the mobile station, depending on the distance, how much do you have to send your data earlier that it exactly will reach the BTS when your time slot, when it's your turn, when the BTS expects your data for the appropriate time slot. So you have to avoid overlapping data. So this has to be precisely synchronized. It's a really strict, simple, fixed TDMA pattern. Okay, that much about guard spaces and time advanced fields. Then inside the normal burst, you see there's a tail, user data, certain additional bits, training data, user data, tail, kind of a symmetric setting here. So what we are really interested in is the user data. 75 bits here, 75 bits there, 114 bits altogether. If we want, we can further subdivide a single slot into 2 parts of user data. So if we use all the 114 bits for one user, it's called a full rate channel. If we only use one part for user and the other part for another user, we call it a half rate channel. So depending on the coding of our data, voice for example, if we code it with lower quality, we can squeeze 2 users in a single time slot. So that's theoretically up to 16 voice calls on one frequency, because you have 8 time slots on a certain carrier frequency and 8 time slots, 2 users per time slot. That's a maximum of 16 users per carrier frequency. These are so-called half rate users. And full rate, maximum of 8 users. Additionally, you will see bit fields as 2 times. This bit tells you if the data is user data or control data. That's the purpose of this single bit. And then you have tail bits, training bits. The idea there is the training pattern is a well-known pattern. And if you receive the pattern, you see how you can synchronize to the time slot, because you know the data, you know the tail bits, you know, oh, now it starts, and you see the training bits. And that means depending on when you receive the training bits, you can synchronize the whole system. And synchronization again is needed for setting, for example, the time advance field, because you will receive data in your downlink time slot. For example, here, time slot number 3 on the downlink, you will receive data. That means you can then adjust your time advance because you know where the training field is. That means you know the delay, and that means you can adjust the delay for your sending time slot number 3. So that's the basic idea. So now you see how we separate up-downlink, how we separate different network operators, how the operators can then use the channels to, well, actually use them in the different cells, non-overlapping if you have the same frequency, etc. And within a single channel, you further subdivide this channel using TDMA, the time multiplexing, and you apply a multiple access scheme by assigning a certain slot to a certain user, or with half-rate channels to 2 users. And you have to adjust the sending time. You have some guard spaces for minor fluctuations, but if you move further away, if you come closer to the antennas, then you have to use the time advance field. So that's the basic idea of how you apply multiplexing for your normal user data. However, if you have a closer look to all this multiplexing, and this is where I will not go into more details, you will see that GSM has many, many more frames, a whole hierarchy of frames. We now had a closer look into this TDMA frame here, repeating every 4.615 milliseconds. We have many more other frames, multi-frames, superframes, hyperframes, etc. Why? Again, without the details, you use these frames then, for example, to code control data into the data stream. So, for example, you can always use a certain slot in a multi-frame to transmit, for example, certain, control bits. So how is this then reflected in your frames? Well, actually, you're stealing user bits. That means although you have to transmit something, the system will simply steal your user bits, not transmitting user bits, but transmitting control bits. You will not hear this because, for voice transmission, you have a lot of forward error correction, coding. You will not really notice this. Also for data transmission, you have forward error correction, so that's not a problem. So you can actually steal, plus you assign certain slots in your TDMA frame also for control data. In each cell, you will find slots for control data. Control data is, for example, used for transmitting things like the number of the cell, the operator, many more control data you need for medium access, you need for synchronization, etc. You also need this hierarchy of frames for the encryption scheme, for numbering, etc. If you're interested in these frames, frame structures, more protocols, multiplexing, etc., please do look up the standards. But as I told you already several times, thousands of pages. So if you're interested in something especially, then look up exactly this, but you cannot simply read through the whole standard. That's way too much. Okay, so now we saw a bit of the multiplexing. And as you know, and used to in all the communication systems, GSM also specifies many communication protocols. Once more, we will not go into the protocols, just for an overview. I already talked a bit about the UM interface. That's our radio interface. That's where we transmit over the air between the mobile station and the base transceiver station. Then we have the A interfaces between BTS, BSC, BSC, MSc. And this is then usually where we have our fixed or microwave connection from the base station to the base station controller into the fixed network where you have all the MSCs. And what you see there is the classical layered architecture of communication protocols where you have classical systems, pulse code modulation on the physical layer. That's what we also use in ISDN. That's for coding our typical 64 kilobit per second, 8-bit per sample or 7-bit per sample voice, for example. Then we have the classical signaling system SS7. That's the signaling system used to connect the databases to forward numbers and all this. And then many more protocols like mobility management, link access procedure for the D channel adapted to mobile systems, etc. These are protocols also used in ISDN, so layer 2 protocols, layer 3 routing protocols, etc. Not internet protocols. So specialized protocols from layers 1, 2, 3 used for routing calls, call forwarding the numbers, setting up a link, etc., etc. Because before you can set up a connection for data transmission or for a voice call, you first have to set up a connection for a control channel. And the control channel is the D, it's called the D channel. B is for user data, D is like delta, it's the control channel, and B like Bravo is for user data. So that's quite typical for ISDN systems. Okay, again, learning protocols, etc. No, you shouldn't do this. This is something you have to look up. If you have to deal with it, look it up. Then you see the packet formats and the bit patterns, etc. and all the protocols, all the rules, etc. This should just give you a rough overview. Some questions and tasks. Please go once more through the channel structure, the slot structure, the architecture of GSM, and understand where GSM applies what type of multiplexing. You will find different multiplexing schemes in GSM. Then how does GSM adapt to varying distances between a mobile station and the BTS? What is the role of the guard spaces? How can you adapt to a moving mobile station? And in this context, what limits the radius of a GSM cell? There are several factors, name them. And finally, what is the maximum data rate per time slot? Look at the time slots, look at the number of bits per time slot, look at the repetition pattern, calculate the maximum data rate, and then you will see, oh, there's a difference to the data rates offered by GSM. Why is there such a big difference?